maths.
Math is very important in our life. It governs the way we live, and there is a story in every number.
This PhD program here in UP Baguio is a supplementing program towards the development of mathematics manpower. It's committed to the pursuit of excellence in teaching, research, and extension service within the university, the Northern Luzon region, and in our country.
We are the only institution offering PhD math north of Manila. And there are very few institutions offering PhD math. But we need researchers in mathematics, and it's not always the case that mathematics researchers and professors are able to go to Metro Manila to earn their PhDs, much less abroad, although we have people already being sent abroad to train for PhD.
Actually, pag mag-PhD ka, na-realize mo tayo palang hindi alam. Ngayon pang dapat matutunan, kulang talaga yung BS and MS math. And if your intention is to teach, do research, do extension work as a mathematician, malaki ang may tutulong sa'yo sa PhD degree. I'm not saying that you cannot do all these things without a PhD, pero marami kang mas maiko-contribute as a mathematician if you have a degree a PhD degree in mathematics.
If you are willing to help improve the quality of programs in your institutions, and you want to contribute to the upgrading of tertiary and graduate mathematics instruction and research here in the Philippines, and you want to become prolific mathematicians, then you can be a student in our PhD mathematics program here in UP Baguio.
Yung opportunities will open up for you once you have a PhD degree, whether you are in the academe or in the industry, depending of course on the field that you specialize in. Kasi sa industry din naman, yung mga unit sa industry, lalo naging highly specialized. Yung degree mo in PhD can help you go into that kind of specialization.
We are training a few breed of mathematicians in this country, which makes them really unique and different from the rest. The others cannot compete with us in the region because we are the only PhD program with a pure mathematics program.
We are into modeling and applied mathematics. That's a strength of many of our young PhD faculty. And so one can say that in terms of applied mathematics, mathematical modeling, and numerical methods, the strength is quite solid. And so, among the programs in the Philippines, I believe that we can sort of take the lead.
So our department aspires to the high standards of excellence in all aspects of teaching, research, and service. The faculty members of our department have collaborated with fellow researchers from other institutions here and abroad. Here in the Philippines, we have UP Diliman, De La Salle University, Ateneo, Mindanao State University, Ligan Institute of Technology. In international collaborations, we have Kyoto University, North Carolina State University, Vanderbilt University, University of Graz, and many more.
Have very, very good mentors in math. So when they do enroll in this PhD program, I'm very sure they will have a very good training in mathematics. We have experts in the different fields of math.
Very prestigious yung program mo kasi mga PhD yung nagtuturo. This is a program that would cater to the needs of the Cordillera and Northern Luzon. And therefore, it's a strategic move for us to have this program.
PhD Mathematics.
Okay. So we have 2 more minutes. Mag-start na kaya tayo?
Yeah.
Pwede na po, sir? Okay. Okay. So maybe we could start. Good afternoon, everyone. So welcome to the College of Science Lecture Series Committee webinar series. So this is actually the 3rd lecture for this semesters that is sponsored by the Lecture Series Committee. So just to remind everyone with the rules of netiquette, so please mute your microphone and then be mindful of the background noise and other stuff. And if you want to ask your question, please put them in the Q&A tab. So I'm sorry, so this is ignore the last sentence. So put your questions on the Q&A tab. So if you have questions, just put it in the Q&A tab, and then later on we'll just read it during the Q&A part. Okay. So just a brief introduction with the College of Science Lecture Series Committee. So the members are the following. So we have the Dean, the College of Science Dean, Dean Javier, and then yours truly. And then we have the following members of the committee. So we have Professor Joel Adawe of the Department of Mathematics and Computer Science, Professor Ashlyn Balangkod, also with the DMCS, but she's also with the Computer Science program. Professor Jocelyn Floresca of the Human Kinetics program, Professor Patrick Peñales of the Department of Biology, and Professor Windol Santos of the Department of Physical Sciences. And also, we did get a lot of help from the following office. So we have the Office of the Public Affairs of UP Baguio, and also with the Systems and Network Office of UP Baguio. Okay. So those are the members of the College of Science Lecture Series Committee. Okay, so the talk for today is actually part of the celebration of the National Science and Technology Week by the Department of Science and Technology. So the week, November 23 to 29, 2020 is actually the National Science and Technology Week. And the theme for this year is Sandigan ng Kalusugan, Kaban, Kaayusan at Kinabukasan. Science for the People. Okay, so for the program schedule, so I think we're right on time. So the talk will be about 30 minutes, so from 3:45 to 4:15. And then after the talk, we have a 5-minute break. So the break is for you to do the survey. So if you want to receive a certificate, you need to include your name and then answer a survey. And then it's also the time for us to gather your questions. So after the break, we're going to have a 30-minute open forum Q&A. So if you have a lot of questions, we'll discuss it during this period of time. And then after the Q&A, we're going to have the closing remarks and the awarding of certificates. Okay. So let me call on Dr. Joel Adawe to introduce our speaker for today. Thank you.
Okay. Thank you, Sir Wancho. And it is an honor to introduce the speaker for today's webinar. And hopefully you will be attending the succeeding webinars that will be handled by the College of Science. Please watch on the Facebook and UP website. Okay. So to introduce our next speaker is Paul Samuel P. Ignacio, and he is our graduate at UP Baguio in 2010. He finished his BS Mathematics, cum laude, and in 2013, he finished his MS Mathematics at the University of the Philippines Baguio before he pursued his PhD abroad. And in 2016, he also finished his MS Mathematics at University of Iowa, and recently finished his PhD in 2019 at the University of Iowa, USA. Okay. And he is currently an associate professor at the University of the Philippines Baguio under the Department of Mathematics and Computer Science. And he has taught graduate and undergraduate courses. And he was able to publish peer-reviewed papers. Recently, the paper classification of single-lead electrocardiograms, EDA informed machine learning in proceedings 2019 18th IEEE conference in Baton Rouge, Florida, and also his recent publication under Darcy, his advisor, entitled Tracing Patterns and Shapes in Remittance and Migration Networks via Persistent Homology, published in EPJ Data Science 2019. And there are several other papers that was able to publish. He was also in books in several conferences, and is
conference talks were his PhD or so classification of cardiography. And other conferences, I think I don't have enough time to read all presentations and their presentations, and he was also able to attend several conferences abroad. Recently, the one in 34th Conference on Topology in Johannesburg, July 2019. Okay? And also the AMS and MAA Joint Mass Meeting in Baltimore, Maryland. Okay? Without further ado, I would like to call on our speaker for today's webinar, Dr. Paul Samuel E. Ignacio.
Thank you, Sir Joel, for that introduction. I would like to start by thanking the Lecture Series Committee for having me and inviting me to do this talk. I'm really excited to give this talk. I'm seeing familiar names in the audience right now. So I'm really excited to share with you what I do with math. And my talk today, let me share my screen. Okay. Can everyone see my screen?
Yes.
All right, so I'm just making sure. All right, so my talk today is about a new area in mathematics, a relatively young field in mathematics. And my talk today is entitled Shapes in Data, an Invitation to Topological Data Analysis. So here's the outline of my talk. So let me begin with some very short message, an advertisement, and then will develop intuition on what we mean by shapes in data, and then what sort of information we get from these shapes. So we will do this with some survey of my favorite landmark applications of TDA out there. And then I'll give a basic introduction to TDA. So we'll talk about the math behind TDA. Don't worry, I know that the audience is a general audience, so I'll talk about everything in general terms, so you'll be able to follow everything that I say. And then finally, we'll talk about some of the things that we're doing in TDA here in UP Baguio. So here we go. So the first thing that I want to say is that series produced a podcast with the same topic. So basically, the things that I'll be saying here are also, you can also listen to this podcast and hear about similar stuff. So if you're interested in doing that, please visit the Cordillera Center website and see Field Notes episode 17, and you can listen on the podcast via Spotify and Apple Podcasts. All right, so much about that. So let's start by developing some intuition on what we really mean by when we say that data has shape or shapes in data. So the catchphrase of TDA, of topological data analysis, is that data has shape and shape has meaning. So this is due to Professor Carlson of Stanford in 2009. And what we do in TDA is that instead of thinking about TDA as thinking about data as just a bunch of numbers with several descriptors, we do is we incarnate we think of data as a geometric object, basically. So every observation in your data set, you incarnate as a point in high-dimensional space where, so say, for example, if you have data and it has several descriptors, so for example, if you consider these data points, so perhaps there's a name in your data or some other descriptors. What we do is we use every descriptor as a coordinate in high-dimensional space. So if you think about it, this data about Aling Rosing becomes a point in high-dimensional space, in this case in R3. So if you have many more descriptors, you have a point in high-dimensional space, in a higher dimensional space. So if you do that for every point, now so there's only 3 points here, but then if you have many, you have like a collection of points in high-dimensional space. And to give it an idea of a general description of the shape of your collection of points, the problem with this transformation is that discrete points have trivial topology. So there's no nothing interesting about just points. So instead of looking at just points, we're looking at the entire collection of points in high dimensional space. And we do that to classify or to describe the collection of points. We endow it with a mathematical object that captures the overall shape of the points. So by the way, we call those collection of points a point cloud because it looks like a cloud, like a collection of particles, right? And we to get a sense of what is the overall shape of the data, we endow it with an algebraic structure that we can examine the shape of. So somehow we use that as a proxy for the shape of the data. So that's what we do here. So instead of looking at the data as just a sequence of numbers, a series of numbers, we look at it as a geometric shape, and then we proxy the point cloud with an algebraic object, and then we study that under the lens of topology. So what kind of descriptions do we expect from that proxy? So these are shapes that are distinguishing features of that object, of that mathematical object, and I'll describe it later in the talk. So these features are those that do not change under transformations or coordinate change, or even if you change perspective. So for example, say for example, this is that object that proxies the shape of the data, right? So this is an annulus, a thickened circle, right? So one way to describe this would be, well, it's in one shape, right? You can go from one point to any other point in the annulus. And then even if you stretch this, so think about this as, say, like a rubber band, right? If you stretch it, or if you contract it, as long as you don't cut it, right? The annulus is still in one piece. So that's one of the distinguishing features that remains invariant even if you stretch or contract the rubber band. Another one is that it bounds a disk because there's sort of a two-dimensional hole in the middle, right? As opposed to, say, for example, a figure of 8, which has two holes in the middle. So those are the distinguishing features. And even if you change in perspective, those features remain. So these are when we talk about shape in data, this is what we mean. We talk about the shape of that proxied abstract object that proxies for the shape of the data. And so why do we do this? Like, so what sort of information do we get from the shape? So here's a very naive example, just to get an intuition of what we are really doing here. So consider the collection of photographs here, and let's assume that there are only really 4 objects here. It doesn't repeat. So we have this freakishly purple person, and then this a flower, and then we have this moon, and then the cloud. So the idea is that these photos are taken in succession, right? And so from just this collection of photos, we are actually able to infer the order of at which the objects appear. So see, if you take a look at this photo and this photo, they have a common object, the flower, right? So it's natural to think that the order should be this: the purple person, the flower, and then the moon. And then if you look at this picture, then the moon is followed by the cloud, but then the cloud is again followed by the purple person. So there's only one way to go about this. If the photos are taken in succession, right, and the photos, the objects of being in the photos are close to each other, then this is the what's the term for that? This is the configuration of the objects, and that's the information that we sort of extract just from observing the patterns. The pattern in the photos, right? So the circular shape is the shape of the data, and we are able to recover that. That's the term that I was looking for. Here's another example. So consider this collection of colors that light up, and they are generated in a hidden sequence. And the idea is we want to recover that hidden sequence. And the thing is, if the colors light up simultaneously, that means that they represent subsequence in that hidden sequence. So seemingly the colors seem to light up in random order, and there's a sort of chaos here. But if we look close enough, and if we assume that if we want to recover some sort of pattern here, let's assume that the colors will light up if they are close by. Okay, so if we do that assumption, then suddenly we see some pattern, right? So if you observe every pair of colors that light up, then we position one color to another. If they light up simultaneously, we suddenly see that the pattern actually loops. Okay, so if we do that, if we position this point close to this point because they appear in one frame, for example, in one snapshot, and then we are able to recover this configuration, and we see that the pattern actually loops, the sequence loops, and this is sort of the shape that we get from here. So what's nice about this, or what sort of information, or is this actually usable, right? What if we can get this shape? Is it actually useful for us? So the thing is, this is actually exactly what this paper did. So this paper examined or studied the place cells in the brain of mice. So in the brain, there are specific regions that are associated to a specific place. If you go to a new place, and then your brain starts associating one place to a specific region or specific cells. So those cells are called place cells. Right? So what they did was they attached sensors in the brain of mice, and then they let the mice run around an obstacle course, and then they looked at the regions of the brain that are basically most active, and then they tracked the let's just say lighting up of that regions of the brain, and just by looking at the patterns, okay, when regions of the brains would simultaneously light up, they considered that association, they were able to recover the shape or the topology or the configuration of the obstacle course that the mice ran around. So if you think about it, it's exactly this one. So you think about the colors as the place cells lighting up, and they light up if they are close by, or the place that are associated to them are close by, then they were able to recover the shape of the obstacle course that the mice ran into. So this is one of my favorite applications of TDA out there. Another one that has been done is the analysis of time series data. So if you have a time series, right, you can actually recover periodic information about the time series. The strategy that we use is called sliding window embedding. So the general pipeline is this again. You have data, in this case a time series. You embed it into a high dimensional space, a point cloud. So what's the strategy in this case? So first you fix a window. So say, for example, this is the window. And the idea is that we will take snapshots of the time series, right? And so that represents that particular local information about the time series. And then we embed it as a point in high dimensional space. So how do we do that? So for example, this is your window. You just select endpoints from it, or end time values from the time series. And then for each value, you will use it as a coordinate in high dimensional space. So if you select endpoints, you have a vector in R to the n. So you have a point in R to the n. So for example, if you choose n to be 3, right, select 3 points here, you get a point in R3. Okay. So again, each window represents a snapshot, a local a record of the local information about the time series. So if you slide the window over, you repeat the process, you get another point. Right? So if you do that over and over again, what you get is you're generating the snapshots as points in high dimensional space. And the idea is that, think about it, if you have two snapshots that are similar, right, they will be embedded in the same point in the high dimensional space. So the catch is that if there is anything periodic about the time series, then it will translate into a cycle in high dimensional space. And that's a shape description that we can detect using TDA. Okay, so, and this is exactly what they did in this paper. This is another of my favorite paper using the application of TDA, and I'll talk about more about this strategy later in local work that we did. They were able to detect the periodicity in time series data that some of the state-of-the-art methods were missed, especially in the presence of damping. So we know now that this can be useful, right? So we can detect data or shapes in data, and then these data give us useful information about the underlying data set. So how do we actually do this? So the math behind it. So again, I will talk in general terms. So sorry. So this will be accessible to everyone. So suppose you have a collection of points sampled from an annulus. So say, for example, the annulus shape that we had earlier, and suppose we didn't know that. We just know it's a sample point, set of sample points, but we didn't know that it's sampled from an annulus, and we want to recover that information. So again, the thing with trivial points is that they have trivial topology. There's nothing interesting about it. So we start adding some structure to it, right? So what we'll do is that if the points are close enough, we'll connect them, right? So to have a judgment call on what is close enough, we need a distance. So that's why the first step is to choose a distance. So this will be a ruler, and we'll judge all distances using this ruler. If 2 points are at most this distance apart, we connect them, right? So that's equivalent to saying that if you put or if you draw balls around each point of diameter this distance, okay, 2 points that are at most this distance apart will intersect. So that's exactly what we do. So there you have it. I drew the balls. If the balls intersect, then we connect them. Okay, so if you do that, we sort of get the general structure of an annulus, right? But the problem here is that there are too many holes involved. So for example, here, there's a hole here, there's a hole here, there's a hole here, there's too many of them, right? And we just want to detect this central hole that is a characterizing feature of an annulus. So one thing that we can do is that we decide that if you have a collection of points that are pairwise connected, then we fill that space in. So for example, here you have a triangle, 1, 2, 3 points, and pairwise they are connected, right? So we fill that space in. So we do that for tetrahedron as well and for higher dimensional objects. So when we do that, we solve that problem of having too many holes. And see here, this central hole is the one that we want to detect. Now we can describe this object, this mathematical object, and this one has features that the topological features of this, or the shape would be, it's in one piece, right? There's only one connected component, and there's a hole in the middle. So there's a loop present inside. So, but there's a caveat in this process. Remember, the first step that we did was to choose a distance. So the question is, do we naturally choose distance d, right? So the thing is, if you choose it to be too small, then these are the same points that we have. But so if your d is too small, then you don't even central hole that we want. Yes, we detect a hole here, but that is not the hole that we want. Right? But then if you choose your your distance to be too big, then we don't even see the hole anymore. Right? So the question is, what is the way, or how do we go about it? Right? How do we solve the problem? What is the right distance to choose? So what TDA proposes is that we don't answer that question. Instead, we just do all distances. So notice that, and why is that? So notice that there's a distance that's just large enough for a hole to appear. So for example, this distance is just large enough for this feature to appear. So we sort of detect it here, and then increase it a bit more. Then we see that there's a distance that's just small enough for it to close up. Right. So if we successively increase the distance, right, and we keep track of the features, the parameter values at which features appear and disappear, then we get a sense of how important that feature is. So let me play a movie for you. So here I do the same, right? So we have these points here, and then the points here, there are as many points as bars here. So the blue bars here correspond to the pieces of the data. So for example, this is one piece, this is another piece. Right? So everything starts off as its own bar here. And then when it starts merging, then we see this only as one piece now, right? So if you look at it, this is really not two pieces anymore. It's only one piece because they are connected, right? So when that happens, one of the bars will die. So corresponding to the point that gets merged to another one. And so if I play, and so I do this continuously, and then at some point we will get red bars. So what do the red bars mean? So the red bars detect the cycles, the loops, the circles, if you will. Then, for example, these two here represent because we're born here, but then eventually get killed off. Okay, so that's why the bars are terminated here. So again, think about the bars as tracking the importance or the longevity of the feature detected. And we get to this bar here, which captures that information. And we know that, yes, the cycle has already been born here, but at just a little more, it will die, right? So if you do that, yes, that hole closes up and that bar dies. But eventually we get to this point. This point captures the main feature that we want to do, as opposed to the previous bars that capture small persistent. We expect this is the main feature. If we continue the movie, and then this will lag a bit, but if you think about it, that feature that was born at time here is still alive here, and then eventually it gets filled in. Okay? And so in this exercise, we see that if we do this practice, the bars that are persistent or the features that are significant are captured by the bars that persist for a long time. So persist here means that the death time is a lot larger than the birth time. Okay, so yeah, so this is the way that we detect those shapes that I was talking about earlier. So this is the way that we do that. The significant features of the point cloud get detected by the significant bars in the barcode. So this collection of bars, okay, let me just wait for the next slide to load. So this collection of bars is called a barcode. Just a collection of bars. And the nice thing about this barcode, so this is the output of TDA, of persistent homology, the main theory behind TDA. The main feature why we can use it for data analysis is that, yes, we are able to detect the shape, and in fact, this output is stable. So what does that mean? If you change it a bit, if you perturb the points a little, if you move the points a little, the corresponding output, the barcode, will only change by a bit. So this is important because now we can compare the output for any two sets of data. Okay, so this stability result is credited to Kornsteiner, Elsbrunner, and Hera in 2017. And also, it's actually an algebraic signature as well. So you might be thinking, well, we capture that barcode. Do we watch the movie every time and then keep track of all the features that's being born in some time? The answer is no. So in our process, as we increase the threshold, for example, if you take a time slice, right, you can actually assign to that object that we create, the triangles, the lines, and the tetrahedron and higher dimensional stuff. If you collect those, you can assign an algebraic object to that. So I'll just say it's a vector space, so it's a mathematical object. And then for each time slice, you will have one of them. Right? And the successive increase in the threshold actually induces maps between these vector spaces. So we have linear maps here induced by inclusion. And the nice thing about these collection is that, so again, these are algebraic objects, these are mathematical objects. And if you collect these objects together with the map, that again forms another mathematical object called a module. Okay? The nice thing about this module is that you can decompose it nicely into this form. So I won't talk about this in more detail, but I just want to say that if you collect those mathematical objects, it forms another mathematical object which you can write nicely. And why is it nice? Well, it turns out that this decomposition follows this form. The bars here that don't die, so these are the features that are born sometime, but then they never die, they are perpetual. You can collect those in one part. And then the features, okay, that you detect that are born at some time, but then they die eventually, you can collect that at another part of it. And so if you think about it, the bars that we extracted earlier when we watched the movie, you can actually compute it. So this is a nice thing, and there's actually an algorithm for that. It's computable by linear algebra. So the key takeaway here is that once you study data and you have an output for it, the barcode is actually computable and it's also stable. So which makes it amenable for data analysis. Let's see if I'm good with time. Okay, I'm not good with time, so let me on. So here are just some of the projects in Baguio. So when I got back last year, I started the TDA group. So it started in August 2019. And so far, the focus of our group has been on the integration of topological features to machine learning. So that's one nice thing about TDA. The shape that we detect, you can actually arrange that as a vector and feed it into a machine learning algorithm that it can use for specific tasks like classification or regression tasks. And another focus has been on the improvement of computational tools in TDE. Because it's so young, there's a lot that we can do, but it's hurdled by the computational tools available out there. So this has been one focus of our group in UP Baguio. So I'd like to boast about this project. This is one project that we've been working on. It's in infancy stage. We're actually waiting for funding for this project, but we have an initial model for this. So what we did is that we took an ECG data, so an ECG data, electrocardiogram data, and then we took specific parts of it, and then we put it in the pipeline of TDA, and we were able to generate a model that classifies your ECG according to specific several cardiac conditions, right? So if you give us your ECG, we can feed it into the model, and then the model gives you diagnosis of your heart condition, whether or do you have a specific heart condition. So this is it's in its infancy stage. The current model performs well in discriminating condition positive from condition negative ECGs, but there's still a lot to improve, right? So currently we have very good true positive rates, but we can still improve it in other areas. Okay, so that's one. This initial model has been presented in September. And I'm giving a shout out and January. I was going to present this work in the conference, and this will appear in the proceedings, computing cardiology 2020. So if you're interested, but there's a lot more to be done to refine this project. Another work that we are very proud of too is on the development of computation. So remember the barcodes earlier, the output of PDA, those bars. The way to compare that the two outputs, two barcodes, is using this metrics. It's called the bottleneck distance, and it's defined this way. But what I want to emphasize here is this is really a pain to compute because you need to consider all bijection. So for each bar, so you have two barcodes, right? You pair up one bar to another, and then you measure distances, and then you have one barcode to another. You pair up the bars, and then measure distances, and then you consider that for all possible pairings. So think about it: if you have a bar with 1 million bars, barcode with 1 million bars, and another one with 1 million, where there's so much combinations to consider. And so this is really, that's why it's called a bottleneck, because it takes forever to compute, and it's the main metric to compare the output of PDA. So what we were able to do is that we were able to develop a new algorithm that bypasses this matching problem. And Maui, this is we are very proud of this name. So this is a name of an Igor God. It's an efficient algorithm for computing dimension, zero bottleneck distance in PDA. So here's just give you some graphs to get an idea of how good the result here. So currently, it outperforms all publicly available implementations of the bottleneck distance. So there are 4 currently. So ours, there's Hera, there's Dionysus, and there's Persin. So as you can see here, so the x-axis here, the number of points in the bars. So remember the barcodes, the number of bars in each barcode, and then here the runtime. So the best state of the art is Hera. And this is the graph of Hera as you increase the number of points. So at points up to 500, we beat it, okay? But we were not satisfied with that, so we computed up to 30,000 points. So here's Hera again, and this is in log scale. So if you think about it, this is really more pronounced, the advantage here. So in terms of runtime, we beat everything else. In fact, even in the computation, the accuracy, ours is actually fast, closer. We provide a closer approximate than any other implementations of the bottleneck distance out there. And in terms of time complexity, we haven't done the theoretical side yet, but the computational side shows that the growth is just linear. So here we got up to 1 million points, and this is the first time that we were able to compare barcode with 1 million points. So we're very happy with that. And this appears in this paper recently published. So if you're interested, it will also be presented in the prestigious conference NeurIPS in December. Okay, so let's see. I don't have time, so let me just mention some of these other projects quickly. So the other stuff that we are looking at, we're developing other clustering algorithms or other in network analysis that are influenced by TDA. So we're trying to leverage the information that we can get using TDA to design new algorithms for clustering or new measures for net. Another one is to leverage the viral phenomenon in signal analysis. I have a student working on this. And then we like I said, the coordinate falls into this one. Well, topological time series, but we're also able to apply this in financial. So stock data basically, and we are also into analysis of images, digits, and text. Okay, so here are just 4 points. TDA is a very new field in mathematics. It's less than 20 years, so there's a lot of many exciting applications. A lot of things that still can be done. It's compatible with data science, so if you're interested with a career in data science, TDA is a good training with that. And there is also a shortage of researchers working in the Philippines. I can name everyone that I know, at least using the both of my hands. So if you're interested to work in this area, reach out to me. Here's my email address. And thank you for listening.
Okay,
Thank you, Sir Paul. So we ask Sir Juancho.
okay, okay, so I think we have like 5 minutes break to gather the questions and also for the participants to do the survey for their certificates. So let's have a 5 minute break.
Sir Juancho, share mo siguro yung video. 5 minutes.
Mathematics is, sabi nila, the backbone of all is the backbone of technology.
Mathematics is the key that gives easy and quick access to science and technology, and an area of knowledge that has vast applications not only to physical or natural sciences but also to social sciences and humanities.
Math is very important in our life. It governs the way we live, and there is a story number.
This PhD program here in Baguio is a supplementing program towards the development of mathematics manpower. Is committed to the presence in teaching, research, and extension service within the university, Northern region, and in our country.
We are the only institution offering PhD math north of Manila. There are very few institutions offering PhD math, but we need researchers in mathematics and it's mathematics research and professors out to go to Metro Manila to earn the PhD abroad. Although people already abroad.
PhD ka, na-realize mo ang dami palang hindi alam. Ang dami pang dapat matutunan. Kulang talaga yung BSMS. And if your intention is to teach, research, kasi malaki ang side. I'm not saying that you cannot do all these things with a PhD. I mean, marami kang mas may contribute as a mathematician if you have a degree, a PhD degree.
Are willing to help in quality of programs in your institutions, and you want to contribute to the upgrading of tertiary and graduate mathematics action and research here in the Philippines, and you want to become prolific mathematicians, then you be a student in our PhD mathematics program here in UP Baguio.
Yung opportunities will open up for you once you have a PhD degree, whether you are in the academe or in the industry, depend on the field that you specialize in. Kasi sa industry din naman, yung mga units sa industry, like naging highly specialized, yung degree mo PhD can help you go into especially.
We are training a few breed of mathematicians in this country, which makes them really unique and different. The others cannot compete with us in the region because we are the only PhD program with a pure mathematics program.
We're back. Hello. Okay.
Yeah, okay.
Okay. So let's thank again Dr. Paul Ignacio for the very interesting talk. We have students here. So
Yeah, hello.
So the first question is from Sebastian Simon. So as I understand, the analysis relies on the periodicity of data. If this is the case, how is TDA applied to ML, given that most tests done for ML are chaotic in nature?
Okay, so i-clarify ko lang the periodicity application kanina, this is a specific kind of data, in per time series data. So yung transformation na introduce natin relies on the periodicity to transform it as a geometric feature. So in general, you don't have to use a time series data. You can use TDA for any kind of data. So yung statement na it relies on periodicity, that's not generally true. If your data is time series, yes, that's true. But in general, you don't need data.
Okay, thank you. So I hope that answers your questions. Second question is from Lee Haviliana. Can TDA be used to detect or find patterns in a sequence of numbers?
General answer is yes. Short answer or the long answer is it depends on how you will represent the numbers as objects. Right? So the tricky part is how do you convert the patterns as shapes. So if the question of detect, definitely the detection, what is the link between the shape and the pattern, in particular for number sequences. I haven't used that.
Okay, so let's continue on with questions here in Zoom. It's from Anonymous. TDA similar to principal component analysis?
In some sense, well, it depends on that. So for PCA, the goal is to reduce the variables. So in TDA, actually, in that sense, it's different. In TDA, we actually don't drop any variable. So we involve all the information in the point, the geometric object, as opposed to TDA that, or in PCA that you're concerned with out variables that are unimportant or with low variability. So in TDA, the focus is we endow we use all bits of information, and we don't forget anything else.
Okay. Okay, so let's just continue with the questions. This one is from Maria Bardiaga. Is it possible to apply DDA in other laboratory imaging like CT scan, MRI, or PET?
Yes, definitely. I've seen the page does that. So if you think about the picture, right? If you have a picture of the brain, I think what MRI captures is the flow of the of blood in the brain. I think I'm incorrect if I'm wrong, but as long as you have a picture and you can represent it as how do I say it? Features that are specific shapes, like the holes, for example, in the MRI, then definitely you can.
So next question from
I don't know what that's so yeah. There are also some questions to be answered because I already answered.
Okay. There's one from Hope Nable. No.
Hello, sir.
Are there methods within TDA that can compare sets or classes or categories of data so that maybe one can decide if a data is of this type or other?
Compare sets or classes. I'm not sure. Like ito ba ay yung data mo ay can you please elaborate more on this, sir? Medyo, just to compare different sets. So
yeah, I think these are categories of data. So maybe there's a way of
classification of classes of data,
differentiating data or sets of data.
So I'm not sure if it's Hassan. So the thing is, if you have two types of data, right? So somehow you will represent one as a geometric object and another one, and you sort of compare them. And so I guess you can do that, but I'm not sure if the comparison will make sense. That's the way to do it.
The next one from Gusto Alanas. Ano pa po ang mga weaknesses and scope ng TDA besides from availability of needs?
Definitely computational tools. So the main workhorse of TDA is persistent knowledge, and the current algorithm for that is very slow. So the complexity is cubic in the number of simplices. So think about it, if you have many points, you have the number of simplices explodes. So if you have many simplices, runtime also suffers. So really at this point in time, one, yung computational tool, and yung two, yung synergy with machine learning. The thing with barcode is that say this, for use of barcode, there's no sense of what is an average barcode. So you have to appeal to another kind of summary that has that specific property.
Okay, there's a follow-up question from Liha Beliana. Do you know of any study or research that uses TDA to analyze the sequence of numbers generated by pseudo-random generators?
I don't. This is actually a good idea. I haven't seen one that does this.
Another question from anonymous attendee. Is the barcode a sufficient statistic?
Very good question. This is a brilliant question. The answer is no. So there are other summaries that have been proposed precisely for that reason. We don't have a sense of what is the statistics for the space of barcodes. So there's this other statistic called the persistence landscapes. The nice thing about that is it has you can define an inner product space there. So you have many properties that so the landscapes would be functions. So you can appeal to that space of summaries instead. And that has a central limit theorem, so it has many properties. So the track that most people do is actually appeal to that instead of the barcode.
There's a follow-up for the question of Hob Nable. Say chaotic versus non-chaotic.
Oh, okay. That makes sense, actually. So you can compare. I think in that sense, you can definitely use TDA for that, because then if you think about it, chaotic data will have features that are not non-significant, meaning small persistence. But then if you have organized data, then it's more likely that you produce more patterns that are organized. So for example, the shapes, the circles, the loops, you have a higher chance of getting those, the more significant features. So definitely in that sense, yes.
Okay. There's a question from anonymous attendee. How can TDA be applied in pandemic or epidemic analysis?
Okay, so in pandemic, I haven't the things I haven't played with pandemic data. So I guess what you can do is, if you think about the pandemic data as a network, right? So one what do you call it? An infected person could be one vertex, right? And then all the susceptible will be other vertices related to it. If you somehow can transform pandemic data into a network, right? You can use TDA to capture patterns within that. So for example, you can also make it directed. So there's actually another branch of TDA that does that. So you can direct, you can make your infected person like the source, and then the susceptible person like the target. And so you have like a directed graph, and then there's a branch of TDA that actually uses.
Okay, so there's a question from the email from Mark Delara of UPLB. Can you measure the bottleneck distance between barcodes from 2-point clouds of different sizes? Say
yes, you can.
A point cloud of 10 points and a point cloud of 12 points. Thank you.
Okay, sorry about that. So the answer is yes. And I think this question arises with a matching, right? So the idea is, what if you have two barcodes that have different number of bars? One thing you can do is you can consider points in the diagonal. So if you notice in my presentation, there's that delta there. So if one barcode has more, you add points in the diagonal to match it.
Okay, next question, more questions on daming questions. From Paul Vincent Botin. Does TDA can be used in geodata analysis? Is there any article citation you may recommend? Thank you.
I think there's one. So I know of another PhD working in the one of the national laboratories in the US. They were using satellite data. I haven't seen their paper yet, but she told me about this last year. So if they finished it, it's probably out there already. So yes, I know some people working on this geodata analysis. I think there's also one person that used like weather data, like they are in typhoons. I think it's out there. I just don't know the title of the paper at the top of my head.
Okay. So another question from Romel Rial. What sort of theoretical results are of interest in TDA?
Okay, so the one, at least for me, and I'm partial about this because we have an algorithm for the bottleneck distance. The thing is, in TDA, one of the cornerstone theoretical result is the stability. If we didn't have stability, we won't be able to use it for data analysis. And that result is written in the language of bottleneck distances. And so there are some critiques on the bottleneck distance. And right now there are other people are developing other ways of proving stability in terms of other metrics. So if you can define a new metric that has better properties than the bottleneck, then I think that's a good result, theoretical result.
Okay. So there's a series of questions from Professor Nable also. So can you comment a little about how TDA can be used when the data is moving, and by moving we mean evolving in time?
This is a brilliant question, because if you think about it, the parameter that we're using is distance, right? Size, meaning. But then there's time evolving data, right? So for example, if you measure data at this time, measure distances, that's fine. And then you measure again at a different time, perhaps the distance are changed, right? So this will go into what's the name? Higher dimensional persistent homology. So for a long time, we're stuck with the one-dimensional persistent homology because there's no available tool to compute the higher dimensional persistence. But now there is. I think it was last year they launched it. You can actually do bifiltration now. So you filter with respect to the distance parameter. You can also filter with any other variable. So for example, time.
Let's continue on with other questions. From anonymous attendee, I'm just curious if TDA can be used also in image analysis.
Definitely. So image analysis. So let me share with you one preprint that I had. So if you're familiar with the popular data set MNIST, so it's a collection of digit images, handwritten digit images. And so what we did was for each digit, we sampled it, and then we computed the dimension 0 persistence there. We used the barcode, and then we used the MAWIG, of course. That's an application of our algorithm, and we were able to show that you can actually predict higher dimensional features just using lower dimensional features, say for example connectivity information. So we were able to classify the digits 0 to 9 with respectable accuracy using only information about the 0-dimensional, i.e. the connectivity information about the digits.
There's questions from Paul Vincent Botin. So probably it's the same question as a lot of graduate students, beginning graduate students. Can you recommend subjects prerequisite to the TDA?
Okay, definitely. So first, for graduate or undergraduate? For both undergraduate and graduate, the one semester course topology, the point set is a good prerequisite. And after that, you really have to learn the algebraic stuff. So algebraic topology would be a very, very good prelude to TDA.
Okay, what softwares can you recommend studying TDA? Softwares.
Okay, there are many. It depends on what you want to do. So I know there's one now in Python that so the thing is, people develop a particular software for a particular purpose. Right? So, for example, there's one that specifically uses it for time series data, one for another type, and I think now there's one that uses it for dynamical system data. So I think there's one package now in Python, and the name is, I forgot the name, I think it's Tomato or something. It's in Python. What it does is it collects all the state-of-the-art softwares out there, sort of like a hub. So it pulls in everything that you can use for many sorts of data.
So it's an open source.
It is the TDA package in R, but in terms of utility, I think the one in Python is more useful or more powerful at least.
Okay, so we have a few more questions. Is TDA work on HIV data?
So I just don't know the form of the data. Yes, so I can't say in more confident that we can. If your goal is to find patterns, then definitely yes.
Okay, so we have one last question from Professor Nable. Are there methods within it that detects corners or tangents? Or
yes, actually, a nice question. So a paper actually that uses a TDA detect curvature in manifolds. I think it was published last year. So the general interpretation of the barcode is that the long bars detect the significant features, and the small bars detect the noise. There was one paper that TDA actually the small bars are also important. Actually detect curvature. So they use I think they use landscapes, and then they pair it with an in-learning algorithm, an SVM, and then we're able to show that you can actually detect curvature. In that sense, the corners of shapes.
so we have more questions coming in. So from an anonymous attendee, can we use TDA to filter signals?
Oh, in the setback, yes. So there's one that we did. This is with another group that I worked with at in Berkeley. What we did was a single lead ECG again in electrogram. So we used the same technique there, and so so what we were able to show there is that we are able to use TD to detect signals for diagnosing atrial fibrillation specifically. Okay, so we were able to produce a model that gives the single lead, and then will tell use the features, and we were able to show that it's able to predict or at least detect signal for the diagnosis of atrial fibrillation.
I think we have already exhausted all the questions. So if you have more questions, you can email Dr. Paul Ignacio. So his email was given earlier. Okay, so do we still?
Okay, share ka sana, sir, pero...
Okay, sige, share. Paki-share na lang. We have more time, I think.
Ay, okay. Share screen. Okay, so ang aking pong email, if you want to learn or if you want to collaborate on this research work, here's my email. I would be very willing to work with you.
So, yeah, sa mga students and yung mga researchers. So, actually, yung today, marami siyang applications. So, marami siyang connections with other research topics. So, interesting work and topic. So, thank you again, Paul, for your time. So, let me just share my screen. Okay. So before I give the certificate of appreciation, let me just thank all the people behind the lecture series committee, and also those people from the UP Baguio offices, the OPA and the SNO for helping us with a lot of technical stuff and for the promotion of the webinar series. Okay, so let me just read the words here. So the certificate of appreciation is awarded to Dr. Paul Samuel P. Ignacio for sharing his time and expertise by serving as a resource speaker during the webinar talk entitled Shapes in Data, an Invitation to TDA. So awarded this 27th of November 2020 at the College of Science, University of the Philippines, Baguio, Baguio City, Philippines. Signed, yours truly, Chair of the College of Science Lecture Series Committee, and the Dean, Dean Javier, Dean of the College of Science. So we will send you the printed copy and the signed copy soon.
Thank you.
Thank you again. Okay, so maybe we could end now. Okay, thank you again for all those participants and for asking your questions, and also for the speakers. Thank you, everyone.
Thank you. Thank you, Paul.
Thank you all for coming.
And
Do you have more questions? No. Okay, so, sir, okay na po.